Okay, hi everybody. Is my volume okay? Yeah. Okay, excellent. I've decided to hold a talk in English out of respect to my Okay, I think there are also some other people in the audience, so yeah. Um, so I've had this idea of starting in an interactive fashion, so I'm going to start by asking two questions, so please bear with me. So my first question would be, how many of you in the audience are working in teams that are actively deploying machine learning to production? Feel free to raise hands. Okay. And how many of you are not 100% sure what does it really mean to deploy machine learning to production? Again, don't be shy. Okay, excellent. So, for example, if you were to Google or YouTube a course on a topic of machine learning deployment, you would probably notice a couple of things. You would probably notice that there is really not that many materials that you would hope there to be, and that most of them are maximally 3 or 4 years old, and that the tools and methods being mentioned in the videos from 4 years before now are at least partially different than those being mentioned in videos from 3 years before now. And same applies for the following years respectively. And I'm sure that you know this is due to the data science and machine learning hype and the R&D that is still very much ongoing. But what I would argue is that the ML, this dynamic change of tools and methods is particularly true for the ML deployment field. And exactly this dynamic change of tools and methods is the reason why I've chosen this topic, preparing machine learning for production. And also the reason why I asked the question is because I have imagined that the presentation will be beneficial both to the people who are acquainted with ML deployment and who aren't acquainted. So just a couple of notes about me. What some could find interesting is that I don't have an official background in math or computer science. I have a degree in environmental sciences. And after I got my major, I was working in a company called Oikon, which is an institute for applied ecology. And it is there that I fell in love with machine learning when I was working on projects related to remote sensing research and analyzing satellite imagery. After this, I've been working in a company called Acquaint, which is a software company that specializes in delivering machine learning-based software. And there I've been part of a very great team. I've been working on a special case of a recommendation engine and on developing on sort of an in-house semi-automated machine learning framework. And also one of the definitive highlights of me being there was that I got a chance to become the undisputed office golf champion. And I see the guys over there, so thank you for the support. I hope your golf has improved a little bit since then. And yeah, now I'm in HT, really enjoying the diversity of the data sets and the projects that Deba has mentioned before me. And honestly, I am yet to fully understand fully comprehend the full amount of the great many things that can be done with this data. So this is the list of the key takeaways, topics on which I plan to share my experience so far on, and on which I hope that at least some of you will get a chance to learn something new. In the first part, we'll take a look at a distance from a machine learning deployment field and then zoom on the individual components of it. And the second part, which is the shorter one, will be a more data scientist. So unlike the traditional data or big data analytics, which help us answer questions like what has happened or why has something happened, what ML deployment and predictive modeling generally helps us answer is what will happen or even sometimes what is currently happening. And when you combine this power with the tools and methods that I will mention throughout this talk, what you get is a machine learning system. And a couple of examples of these ML systems that are really good at predicting what will happen or what is happening are fingerprint detection, face detection, recommendation engines, and things that are possibly some less known to wider audience is that a lot of companies are spending their resources to internally boost some of their internal processes. For example, they might want to boost their legacy customer relationship management software with ML system in order to better manage their sales, churners, and so on. Speaking in more general terms, these systems can be divided based on their training and scoring frequency. So based on training, we can differentiate the batch training system, in which models are trained in batch fashion, and in real time, or which is also called online scoring fashion. So batch is where you retrain your model every couple of weeks, every couple of months, and online is the type of training where the model gets incrementally trained as with each new data points arrives. And the same thing, the basic differentiation can happen based on the scoring. So the batch scoring and the real-time scoring. And the real-time scoring can further be differentiated as either centralized or edge, where edge is the type of ML system that comes embedded with your software application on your device, and it gets triggered when you want to use it, when you want to unlock your screen. And centralized is a type of system where you deploy your ML code on some local or cloud server, and then you find some means of communicating data and information between the server and the customers. Let's continue with defining what is ML deployment, and let's start doing so by defining what ML deployment isn't. So from my experience so far, what I've observed is I've observed a couple of patterns of usage of ML algorithms, which I don't consider ML deployment. So there are these companies that equip themselves with data scientists, math or computer science experts, whose goal is to solve some business problem in the most optimal way, with a special emphasis on model quality and runtime performance. So these are usually consulting companies like McKinsey, who specialize in one or couple of domains, and they sometimes just deliver the code of the solution, and then the client just does whatever it wants to do with this code later on. Then there is the academia and R&D departments, which kind of do this similar thing, but only for research purposes or for the purposes of developing algorithms. And last but not least is that there are a lot of companies that are kind of doing ML deployment, but they don't really have the full system properly set up. There is still a lot of manual processing going on, not proper monitoring tools are implemented, and these sort of things. So the way I see it, ML deployment is a continuous process. This is not something that stops when you deliver the ML code. There is a lot of maintenance that needs to happen after that. And as I will later show, there are different approaches, different architecture approaches for ML deployment. But what I think is that all of them have these four key components as part of them. And these are the evaluation, deployment, monitoring, and lifecycle management. Oh, sorry. So deployment, evaluation is part of the process where teams experiment, test, and create the model. Deployment is where you save the model and in some way integrate it with either business or a software application. Monitoring is something that should be a key component of any ML system also, and this is, among other things, what this does is it keeps track of how your model behaves over time. And finally, the lifecycle component, lifecycle management component, is the one that kind of encompasses all the components before, and with the addition of automating things like model retraining, managing different type of model deployments like shadow deployments, A/B testing, and etc. So it might also be helpful to look at ML deployment as it is shown in this picture, as something that is circular and that in a sense has no end. So you deploy what you evaluate, you monitor what you have deployed, and you manage your deployments over time. And so these things that I've mentioned are core concept of a term called CD4ML, which is something which is short for continuous deployment for machine learning. And this is something that I've been seeing a lot, at least recently on the web. So if you want to hear more about it, you can Google it. So in the next 10 minutes, I'll take a deep dive into each of these components individually. And regarding the evaluation, if we take a look just at the model evaluation metrics, so just a couple of notes on my experience so far. It is okay to track multiple metrics, but you should really only focus on one, on optimizing your model on one, especially in the beginning to make things much easier. If you're working in an industry, you have probably realized that model accuracy as evaluation metric isn't really that helpful due to the because a lot of business use cases depend on imbalanced data sets. You know, the whole example of the fraud detection system in which you have a fraudulent activity happening 0.1% of the time. You predict everything is non-fraudulent, you get 99.9% accuracy. If you're working, for example, in anything related to marketing or sales, you have probably heard of the lift metric. So this metric is very popular among managers, because it is very intuitive and it kind of, as default, comes something that is suitable for marketing campaigns. And what this tells you is how many times your model is better at guessing things than if you were just to randomly guess it. But I'm sometimes wary of using this metric as comparing models, especially over time, because this metric can be dependent on changes of the ratio of positive and negative values in the target variable, in the cases of binary classification problem. So what I do, and I'm sure most of you also do, is the area under ROC, area under the curve, or the precision recall curve. And here, what also is kind of my conclusion, that in data sets which are particularly imbalanced, I find precision recall even more useful, because unlike the ROC, it has the precision on the x-axis, which compares the ratio of true positives and false positives. So if your model, as I'm telling you on your test set, that you have 10 true positives and 500 false positives, this is something that will look very ugly on a precision recall curve, but you may not even detect it that much on the ROC curve. So these are all examples of offline evaluation which happens on your test set. When you deploy your system, you do online evaluation on your live data, production data. And this you do sometimes with other type of metrics which are called the business metrics, okay? The things that managers could be more interested in. The click-through rate change, the churning change, the user engagement change, and these sort of things. So there is distinction between offline, online, and business and model evaluation metric. Testing, in this context, are all of those things that you should test when you're deploying an ML system, which aren't part of the model evaluation. So this hierarchy here is an example is the case of a very complex ML system, which also assumes the integration with a software application. But in reality, a lot of ML systems do not require this integration with software. So in these cases, you can just disregard the green triangles. But starting from the bottom left, the data engineering pipeline is, among other things, the tests in this pipeline need to assure that the data that gets to the data scientist is 100% correct. In the ML machine learning pipeline, what you should also be doing are the unit tests. So if you're doing proper ML deployment, you're writing classes and functions, right? And if these are complex enough, what you should have is unit tests for each of them. So at future, you can just have, within a click of a mouse button, a test that will tell you if any other changes you made to the code aren't affecting the behavior of your class or your function. And one other thing that is also a strictly part of the ML pipeline is the data checking and the data coercion process. So, for example, imagine if you have deployed your ML system and you have live production data coming in, and in one of the variables, which is a categorical feature, is one category which wasn't there when the model was trained. So if you haven't anticipated this and somehow solved for this, what will happen is that your code will break. And luckily, some of the scikit estimators, transformers, and so on do have an option to deal with this problem automatically. But if you're not using any of these things, this is something you will need to solve manually for each of the features you have in your training set. I will skip the software tests. So after all of these three types of base level tests are finished, you move on to the higher hierarchy tests. So between the ML pipeline and the data pipeline, what happens first is the model evaluation, which I mentioned last slide. And what sometimes you also need to have is to test the model for bias, to see if there are any unfair assumptions that your model is making based on the gender, based on location, or whatever. And between the ML pipeline and the software code, what you need to have sometimes are the construct tests. And these are the types of tests that ensure that the communication between the ML parts of your system and the non-ML parts of your system is intact and always okay. And moving even higher up are the integration tests and the functional end-to-end tests. So I see the deployment component as also a two-step process, in which the first one is where you save the model, and the second one is how you integrate the saved model with either business or the software application. So the need for model serving is very intuitive. So model training can take a lot of time, and you of course want to save your model to use it on production data. You don't want to retrain it every time. And this in Python you can do very easily using the joblib library and the pickle serialization format. So you can see on this pseudocode example here that this is actually just a one-line code, joblib.dump. And this is actually a really good example because it demonstrates that you can not only save the whole the model only, but the whole pipeline object. And for those of you who don't know, the scikit pipeline class is a very, very useful tool to master. So this pipeline class allows you to bundle up all of your pre-processing steps, like different types of encodings, a PCA, scaling, etc., into any order you want into this pipeline. And then what you could do is you save your pipeline and load it and use it on production data. And there is also another option, which I've been using also, and it gives you kind of even more flexibility, but also assumes some objective-oriented programming skills, is you can wrap your whole pipeline, and in this context, I'm not talking about the scikit pipeline, but the pipeline in general sense. You can wrap your whole pipeline in a wrapper class, in which you dump all of your artifacts and objects you have created on training data, you dump it to the wrapper class, and then you pickle this class and load the class to use it on production live data. Besides pickle, there are also some other options, but I will not go into details about them. So integration is one of the most fun parts of the whole ML deployment process. And I think that there is still no single best way to do this, because the use cases and integration requirements really vary a lot across companies. And therefore, in reality, even though there are more architecture approaches than I have shown in this table, these four, the real-time streaming, the embedded approach, the shared database approach, and the web service approach, I think are the four main ones and the four ones that are most commonly used. They, of course, differentiate by a lot of factors, but these five are, I think, the most important. So starting from the real-time streaming, this is the approach that is most complex, requires the most resources, and it relies on tools like Kafka and Spark to deliver results, huge amounts of results with very low latency. And it uses usually message queues, some types of message queues for communicating between the ML code and other parts of your system. The embedded approach is the one that comes bundled up with the software application. This one also needs to have very low latency, and the communication happens usually using some in-process API you have created. The shared database approach is the simplest one, and I think this is the one that the most companies are using. And this is where you have your that legacy system that I mentioned, the customer relationship management system. That system sits on top of some database. And you have this database and your ML system on the other side, and then you have your ML system pushing the results to your database, which then gets picked up by your legacy system. And finally, the web service approach is the one that I think offers the best trade-off in sense of complexity and flexibility. And it is based on something that is called REST API, and I will talk about this more later. So regarding the real-time streaming approach, this is a really complex topic, and I think it should have only whole meetup only for this. So I will not go into more details about it. The embedded approach is not something that I've been a part of a team that was working on it, so I will not mention it also more. But I think it is in a way similar to the web service approach, and the shared database approach is very simple. So I'll skip that too. And in the next couple of slides, I will be talking about the web service approach based on the REST API. So this here is an example of how ML deployments can sometimes look like. So on your left side, you have your data scientist who is doing his own thing in his own language, but basically what he's doing is he's writing the recipe. On the other side, you have your developer who needs to rewrite this in his own code, which is being used in production. And you can see right away that this is not the most optimal thing to do. You have the code rewriting. But what also can happen in this context is that data scientist doesn't always fully understand what can be translated to production, what can be translated to the developer's code. And also, data scientists in this context sometimes do not think about the scaling issue of the code. On the other side, the the developer is not necessarily acquainted with the understanding of the business problem, and this can also cause some misinterpretation when translating the code. And what can happen in the end is the developer can end up writing a completely other model than the data scientist has intended to. So then comes the REST API solution to the web service approach to the rescue. So you can see the REST API is sort of a language agnostic contract of sharing information between the machine learning code and the non-machine learning code. Okay, so it breaks down the wall of confusion. And for those of you who don't know, I will just explain these terms just to give you a bit of context and to understand how this approach works. So microservices are a software development technique which is very commonly used nowadays, and it allows you to dissolve your application components in a couple of loosely decoupled components which are called microservices. These microservices communicate between each other using the APIs. And the API is short for the application program interface. And this API is something you build on top of each of your microservices. The web service is a type of API that uses the HTTP protocol for communication, and the REST API is just a pretty commonly used type of the web service. So besides the breaking the wall of confusion, there are some other benefits of using this approach. So you can have a lot of different types of Python code wrapped in your API. And for example, some ML solutions can be actually consisted of multiple models and multiple business rules connecting them. And you can bundle up all of this code just in one API. And what also is very beneficial is that this solution allows you to scale and to be fault tolerant, because you can multiply your machine learning microservice to many nodes. Everything nowadays is in a cluster. So you multiply it to multiple nodes, and you have one node stops working, you have the other one backing it up. And what microservices solution generally offer you is the way to decouple your code, so you can just more or less safely work on one microservice without necessarily affecting the behavior of other ones. Monitoring is kind of the least interesting part of the whole ML deployment, but you really do need it. So first and foremost, you want to find out how fast does your model decay into production. When do you need to retrain it? But there are also some other things that you might be interested in. How do code changes affect the runtime performance of the model? How to, you might want to monitor user feedback and include that in your model. You might want to detect where the model is underperforming and these sort of things. So to answer these questions, what you need to monitor is the statistics about the train, test, and live production data. Statistics about the probabilities, the outputs of the model, the statistics about the metadata, the change of business rules or processes that affect the behavior of the things you're modeling, and also a couple of other things. And what you also may want to end up having is creating an alert system which will notify you if the inputs to the model or the outputs of the model are significantly different than from what you would expect. And this is especially true for online learning models. So if we again take a look at a distance at ML deployment, we see that it's just part of a business problem. So you as a data scientist are concerned with your model evaluation metrics. Your manager on the other side is more concerned about the business metrics, and he will evaluate the performance of your model based on his metrics. Same is for the CEO. He will have his own related revenue metrics, and some companies even go one step higher. They want to monitor the effects of what their ML deployment has on communities and societies. So think Google or Facebook and their systems. So my point being here is that the higher the effect, the order of the effect is, the harder it is to monitor it, and the harder it is to correlate it back to the behavior of the model. So currently out there are numerous tools being actively developed for monitoring purposes, and MLflow is one of the most prominent ones. So it is really a great tool. It can be used in R, Java, Python. It integrates well with Scikit, with Spark. It can work locally on a cluster. You can manage whole projects with it, and it comes with a very neat user interface. So in this pseudocode, you can see that tracking logging parameters and metrics in a machine learning system is something that can be done very easily, and something that you can track on this on this user interface. Docker and Kubernetes are tools that the software developers are very, very acquainted with. So they are the kind of tool that is necessary for any agile development. And what Docker allows you to do is to bundle up your whole application, all your dependencies, code dependencies, libraries, in a thing that is called a container, and then you can push this thing on Dockers, multiply them, create microservices from them, and so on. In some cases, your ML system will grow bigger, and you'll have many of these Dockers to manage, and this is where the Kubernetes comes to the rescue, because it is an orchestration tool for managing the Docker images and files. So if we consider for a couple of minutes, why is ML deployment hard? So this here is an image of a classical image of the ML workflow project. And if we take a look from the tools that are being used perspective, this might give you a better sense of why things can get really complicated. So the data engineers are using their own tools like Hive, Mongo, Hadoop, Oracle, and so on. Data scientists are using Python, R, KNIME, SQL, Desk, Pandas, etc. Developers are more versed in other languages and tools like Mesos, Kubernetes, Dockers, and all of us are using the management tools like Jira, Git, Bitbucket, and so on. And since ML deployment is a very continuous process, it is not easy to connect all of these tools in one continuous workflow. It is probably impossible, but what you need to do is strive to make it as automated as possible. These here are a couple of key takeaways that I had from a very interesting article titled Hidden Technical Debt in ML Systems from Google in 2015. And what they did in this article is they analyzed how much of their internal resources are they spending on ML code compared to all the other things that are required in order for the ML system to run. So to be fair, it's Google, so their ML systems spend on hundreds or thousands of nodes, but this really, puts things into perspective. How that ML code is only just a part of all the things that need to be also there in order for the whole thing to run. What was also interesting for me is that they argued that the machine learning deployment can be even harder than classic traditional software development. So there are additional tools and expertise that you need to have. There is the research component included, the reproducibility component, the GDPR issues are bigger, you have higher hardware requirements. And one of the key takeaways was actually a term that they used, which they called depth. And for example, dependency entanglement depth is something that stacks up over time and creep up behind you. So you have not only dependencies between libraries, between software versions, you have also dependencies on models over data. And this thing, what can happen for you if you have your ML system set up and you want to change only one small thing, you may realize you need to change much more than that one thing in order to keep things still working. There is the reproducibility depth and the analysis depth, which was also interesting to me because what sometimes happens is that when you deploy your ML model, your model actually starts sometimes to affect the very same thing you are modeling. So how do you measure that? How do you account for that also? And just to summarize this first part, so having all these things in mind, how do you choose the best approach? So I think there is no answer that will start with anything else, but it depends. But I think that your solution, your approach will lie somewhere on this 2D plane between the 6 points. So what are your train and score frequency requirements? What are your scaling requirements? What is your implementation cost? What is your flexibility and integrability? You may want to ask yourselves, how easy would it be for me to switch to another algorithm, to another library language, to move the whole thing to a new cluster? How much interpretability do you need? How much accuracy do you need? Do you really need that 0.01, or are you more concerned with the data, with the model runtime? Yeah, and these sort of things. So the second part is HT related and more data science related. So when I came to HT a couple of months ago, my dear colleague Marira and I, we decided to really step up the game of machine learning in HT. So we decided that any future project we're going to be working on, we're going to guide ourselves on a couple of guiding principles. So we're going to keep things as modularized as possible, and we're going to, of course, write functions and classes and use the things to be reproducible as possible. What we also decided is we're going to create our own multi-purpose machine learning framework that we're going to use for any future binary or multi-class problems that we're going to encounter. And that this framework is going to give an output that is immediately going to be usable as something that can be shipped to production. So the first use case we apply these principles on is the churn use case. Now, for those who don't work in the telecom industry, this use case may sound simple, and it's true. It's not the most complex problem in the world, but consider for a fact in HT. So we have different types of of packages, services, our own internal categorization of things. So either users can be either fixed mobile or fixed and mobile. Users can be prepaid or postpaid. Users can be 1P, 2P, 3P. You have the household effects affecting of your models. So my point is, what of these things do you want to model? Do you want to model each of these things specifically, or do you want to somehow group them up or whatever? And the second thing is the issues, the dilemmas with the data. So you have large amounts of data, and some of this data is on 15-minute interval, some is on hourly, daily, monthly, and so on. So you need to, if you're going to use monthly, you need to aggregate everything on monthly level values. And the other thing is that, this monthly data comes with a 50-day delay. So this means that you're going to get your training data to score churners for the next month in the middle of the next month. So you lose 15 days of churners right away. And then you also take into account the, couple of weeks that the marketing department needs in order to prepare the campaigns. You lose even another week. So then you realize you need to change your target variable. You need to predict churners that will churn from 2 months from now, because you have 1 month that you're going to lose anyways. So also you have different type of churners, which also cause some issues in this whole thing. And then you ask yourselves in the end, so we have a monthly model. Why don't maybe we also need a weekly model or a daily model? Maybe we want to have something real time. Then which of these do we choose? Do we combine them all together, or a lot of different options you need to take into account. This is something that was very, very fun for me, because when we started doing this churn use case problem, we had a brainstorming session with our team, which is partially from Brazil, Croatia, Poland, India, and so on. And we were all throwing our ideas. There were some juniors who were also throwing a bunch of ideas. And what we ended up is a list of things that we maybe want to experiment with. So each of these rows is something that we wanted to possibly experiment with. And a lot of these rows are actually could be part of any ML pipeline, okay? But the things you may generally want to test with whatever the problem is. And as you know, each of these options or components has at least a couple of options inside them. And if you just think about the whole data science rule, there is no such thing as free lunch. This means that, one sub-option of one component may not work the same if you change any other sub-option of any other sub-component. So you need to test everything with everything. So in theory, if you would really to do that, you would end up with 900 million things to test. And now, of course, even a junior can decrease this a lot. But my point here is that you need someone with experience who can tell you, we have a deadline in 2 months, and these are the things we're going to experiment with, and these are the things we're going to possibly do later. So our framework was based on a nested cross-validation approach. So this is a very, very powerful technique. So if we think for a minute on the general data splitting approaches, there is the train and test split. But from my point of view, this is a very common mistake that people are doing. Because if you're going to do hyperparameterization or feature selection on the training set, you are going to be doing the model selection and testing this on the test set. And then you're going to use the same test set for evaluating how do you expect your model to behave on live data. So you have bias. You have same test for model evaluation and choosing the model. So for these purposes, of course, what you do is split on training, validation, and test split. Validation is used for model selection, and test is used for reporting. The other thing is the cross-validation, also the normal cross-validation. So what this thing offers you is when you don't have gazillions of data points, to split your data, to use each of your data points both as training and as testing over different loops. But this solution also suffers from the same thing that suffers the training and test split. So this solution also uses the same test set for evaluation and model selection. And this is the reason why we have used the nested cross-validation. And what this approach does, it separates your process of model evaluation from model selection. So you have the outer cross-validation loop in which you use for evaluation and the inner loops which you use for selecting the model. So just for an example, in a 5-fold cross-validation, what you do is you take 80% of your data and leave the 20% aside. And then this 80% of your data, you distribute, you forward it to each of your hyperparameter combination or any other thing you want to test. And then you do this inner cross-validation for each of the hyperparameters using the 80% of the data. You have selected then your best model, and then you still have left your outside 20% to report to see how can you expect this model to be behaving on live production data. And this all happens k-fold number of times, okay? But you can see probably right away that the issue with this is that this can be computationally very intensive, because this means you'll have to have model runs equals to outer k times inner k times hyperparameter combination things to test. And for these purposes, what you need to do is leverage the power of parallelization, so either locally or on a cluster. You probably, those of you who are using scikit library, you probably know that there is the njobs parameter, which allows you to distribute your work, your modeling, on any number of CPU cores you want. But in our case, we didn't want to only parallelize the modeling. We wanted to parallelize our whole pre-processing step, parallelize as much of the things as we can. So what we did use is a library that internally comes with a Python, which is the multiprocessing pool library. And what we did with it is we created our own cross-validation function, and we have distributed this function to all of the pool of the workers that this pool class creates. And it then distributes this. And this is just this is not a pseudocode. This is exactly from our framework, and this is all the code you need to distribute something that is as complex as cross-validation on your CPU cores. On cluster, you have things that are getting taken care of for you because Spark parallelizes things for you internally. And also related to this is the issue of data leakage. So data leakage happens when you use your pre-processing on your whole data set instead of individually on train and test set. So you use information from your test set, even though you should really behave like your test set is non-existent until you are finished with everything. So these circles are the things that introduce data leaking, the feature engineering, the imputation, the encoding, the scaling, the data set balancing, and so on. So this means that each of those things needs to be done separately on training set, on validation set, and on test set. And when you combine this with the computation intensiveness of the cross-validation approach, you can see that it gets crazy computationally intensive. My point here is that these circles, some of them cause minor, really minor data leakage. Almost, you can probably disregard it. So at some point, at least I asked myself, do I really want to be the perfectionist and do everything for the MVP at least 100% correct, or maybe do I, want to do, for my purposes, not be the purest perfectionist. So this is the project structure of our multipurpose framework pipeline. So we have done our best to keep things modularized, we follow a common data science project structure. And what we did with this multipurpose framework is the following. So this pipeline is based on nested cross-validation approach. It works locally and on a cluster. It will work for any binary and any multi-class case. It outputs model that is ready for deployment. It parallelizes much of the workflow. It aggregates visualization for all of the folds, which is something that I will show soon. It offers multiple options for decision threshold optimization, multiple options for evaluation metrics, for reporting, and for pre-processing options. So any of them you can choose, and the framework will do its own thing. What we plan to do yet is to combine these two frameworks into one single file to extend the framework to work not only on XGBoost, but on any scikit algorithm, and to implement option to be using multiple models and the option of stacking the models. So for the end, just this is one of the outputs of our multi-nested cross-validation approach, and this is an example of a solid model which has AUC 0.83. But you can see that here are plotted all of the AUC cores of each of the fold. And you can see that the model is very stable because there are no much oscillation between the curves. And then we also have all other important metrics like the averages of the metrics, like the log loss, the F1, the average of the confusion metrics for all the folds, and etc. And this here is just an example of a poor model with poor AUC and one that is not stable enough because you can see the standard deviation. And yeah, this is one of our results besides the pickle format, and we are planning to even develop this further and to use this for most of our future projects. So yeah, thank you for the attention, and please ask some questions. Shoot.